Let me illustrate how to work with the implicit function in an easy case where the function can be written also in the explicit way. Consider the equation x squared plus y squared minus 2 is equal to 0. This is the equation of a circle with radius square root of 2. And consider the point x0 is 1, y0 is 1. It is not possible to consider the entire circle as a graph of a function. But if we choose only the upper part, then we can express this in the explicit way. Because if we write y squared is 2 minus x squared, then assuming only non-negative y, we can write y is square root of 2 minus x squared. This is not the whole circle, but it's okay if we are just interested in some neighborhood of the point 1, 1. If we have this explicit way, we can compute the first, second derivative as you like. So let's do this, and then we will use the implicit function machinery to compare the results. And this machinery for the implicit function is very important, even if this approach is not possible, because this function, this expression is too complicated. So what about, well, we can check the value at x is 1, 2 minus 1 squared is 1. Now what about the derivative? If we have the function like that, then the first derivative is derivative of the square root, which is 1 divided by 2 times the square root, times the derivative of the inner function, which is minus 2x. And then we can evaluate, we can reduce by 2, and then we can evaluate the derivative at the point 1. 1 minus 2 divided by 2 is minus 1. We can find even the second derivative. Which is the derivative of this, so let me reduce by 2. And let's write minus in front of the fraction, and we have 2 minus x squared. And here we have the derivative of x, which is 1, times the square root, 2 minus x squared, minus x, and the derivative of this is again the fraction, which is minus, so minus minus gives plus. Here we have 2 minus x squared x. This can be simplified a little, which is not important for the moment, and we can evaluate the second derivative at 1, which is 1 plus 1, which is 2, divided by 1 is 2, and minus 2, so the second derivative is minus 2. So this is nothing new. This is just how to differentiate the function, well, from the first semester. But now, let's have a look at the function given in the implicit way only, which is very important if this computation is not possible. Imagine that this equation is so difficult so that we cannot write it this way. We cannot express y in terms of x. This formula is just not available. But only the formula is not available. But the function, in the sense the dependence of the two variables, is there. Y depends on x. Just we have not the nice formula for that. We have no formula for that. So if we consider y to be a function of x, then having the equation x squared plus y squared minus 2 is 0, we can write it x squared plus f of x squared. And now we can differentiate with respect to x. Or perhaps we should check the conditions. If we denote the left-hand side as capital F, well, this is a polynomial, so this is a function defined in entire R squared, and it is continuous, and it has continuous derivatives, so we can say that f is from the class C infinity R squared. This is the set of all functions that are continuous and have continuous derivatives of any order. This is the best situation that can occur. Now when we differentiate this, the derivative of x squared is 2x, and derivative of f squared is 2f times the derivative of the inner function. The inner function is small f and its derivative is f prime. Minus 0 is equal to 0. We can divide by 2. And if we subtract x and divide by f, we have the formula for f prime. Well, and then we can evaluate the derivative at the point x is 1. X is 1, and fx is given, this is y0, which is also 1. So, you see, fortunately, the same result. There is a little price, a little fine. If we want to evaluate the derivative using this implicit function theory, then often the information about x is not enough. We must have the value of x and the value of y. This is a typical situation. This was not necessary when treating the function as the explicit function. Here we can find the value of the derivative from the information, based on the information on x alone. Alternatively, we can come to this derivative using the formula that f derivative is minus fx fy. Because when we have capital F being x squared plus y squared minus 2, then the derivative with respect to x is 2x, the derivative with respect to y is 2y, and either we can evaluate these two derivatives at the point 1, 1 to get 2, 2, and then we have minus 2 divided by 2, which is again minus 1. Or we can postpone the evaluation, and we can find that the first derivative is minus x divided by y, where y is a function of x. And we can differentiate this once again with respect to x. Derivative of x with respect to x is 1 times y minus x, and the derivative of y is y prime. Y prime is actually an abbreviation for small f prime, the derivative of the implicit function. And then we can evaluate the second derivative at x is 1. But this time you see the information about x is not enough. The information about y is still not enough. We must have three numbers: the value of x, the value of y, and the value of the derivative. But fortunately, we have all these information. We have that x is equal to 1, y is equal to 1, and we have found in many ways that the derivative at 1 is minus 1. So, using these three pieces of information, we can evaluate this expression. Y is 1, so this is 1, and here we have y, which is 1, minus 1 times minus 1 is minus 1, so 1 plus 1 is 2, and we have minus 2, minus 2, minus 2, yeah, which is in agreement with the second derivative computed using the explicit function. Well, and if we have the second derivative, we can differentiate this formula just looking at y as a function of x, and in this way we can find the derivative of any order, even for a function for which we have not the explicit formula available. This is a very strong result.